So one of the things that's interesting about the field is it's not a discipline in the sense, right? It's like 500 intellectual disciplines all tied together flying at different speeds. The people who built the internet had the idea that it was going to be a general purpose network. So what's important about that is not just that it can do anything that you want to do today, but that it was able to support things that nobody had invented yet. So you got to remember, this is 1990. The web hadn't been invented yet. We had email, but that's it, right? So when the internet was created, that was the extent of the applications that existed. And yet the people who were working in the space, I wouldn't say that they foresaw the World Wide Web or Facebook or Zoom, stuff like that. But what they did foresee was that if they built a technology that was designed to be flexible like that, instead of dedicated to a specific use, that it would, over time, change the world, which I thought was pretty cool. My degrees are in electrical engineering, which is sort of the electronics and hardware side, not computers per se. And around I guess it was probably 1982, the thing that we used to call VLSI, right? This is chips, integrated circuits, right? The way those things happened at that time was that there were 5 people in the world that knew how to do it, or 50 or something like that, and they lived, in the dark caves of basements in a few places. And some people came along, two or three people came along that were critical to this story. There's a guy named Carver Mead and a woman named Lynn Conway from Caltech, and then Danny Cohen from ISI, who's going to come into this story. Carver and Lynn worked out the intellectual story of how, instead of having it to be a black art where every single person who made a chip had to know the whole story, and every technology that you used was different, and there was no commonality, you couldn't go back and forth, so they couldn't teach it, nobody could teach it. It was something you picked up as an apprentice somewhere. Carver and Lynn came along and said, no, we can kind of turn this into a discipline, to an engineering discipline, and we're going to invent a way that anybody will be able to design circuits and build them. And Danny came along and said, well, that's really nice, except if you want to actually build them, we need some kind of a foundry. We need some kind of a technology that will let you specify your circuit and build it, right? And that's what became MOSIS. Here I am, a young grad student setting out to build these integrated circuits, and I got kind of ambitious. And I wanted, the idea was you would build it's a class, right? So you build a little toy thing, and I'm like, no, I'm going to build a big one. So it turned out I needed more computing power than I had sitting, available to me. So I set out to steal everybody else's computing power too, which means this thing called a computer network, right? So this is the things that connect computers together. And I ended up sort of designing a thing that let me borrow other people's computers when they weren't using them, connected them all together in a network, and built the big chip, which did not work in the least. But it got me into computer networking, which has been my professional field ever since. I joined ISI because of the collaboration that I had told you about. So, there was a small group of people, particularly a guy named Bob Braden, who you may have heard his name. He is no longer with us, but he was one of the people in the ISI team. And Bob's role, Bob was a very major figure in the internet community. He wasn't one of the sort of fathers of the internet. But the thing that he did was a lot of the social connection. So Bob was the guy, he was very, very good technically, but he was also very, very good with people, which isn't necessarily a skill that your average geek has to spare. So Bob would bring people together, he would organize groups to work on stuff, and he really created at one point this thing called the End-to-End Research Group, which was a bunch of people that were kind of self-selected. To become a part of it, you had to be invited by the people who were already there. It's a clique, right, of people who were doing this internet research. And I had been part of that collaboration for a long time. And there came a time when ISI needed a new director for their networking division. And Bob, completely unbeknownst to me, started lobbying for me. And so I got a call out of the blue from Herb Shore, who said, so Braden says I have to talk to you. And I came on out. It was about a 6-month decision. The first time I got wind of Bob's plot, I was out here for a meeting, and Bob said, "Can I just," he wasn't the kind of put your arm around you guy, but he did the Bob Braden equivalent of putting his arm around me and taking me off in a corner and said, "So I did this thing. I'm an East Coast boy. I've been in Boston for 30 years. My wife is in Boston and very anchored in the East Coast, and not inclined to move to Los Angeles. So, I took a long time. I have to say I probably drove people nuts. Took a long time sort of thinking about it. And took the job on the deal that they would accommodate the fact that I was going to be bi-coastal and back and forth. I kept a visiting appointment in the East Coast. My wife has a visiting appointment at ISI, and I signed an agreement with Herb to work here for 3 years in 2005. So something may have gone off track in there. I can't quite remember, but 3 seems a little less than 15. But but that's how I got here. My personal big question was, well, how are we going to, after, when you've started off by sort of contributing to the invention of the internet and changed the world that way, what's your follow-on act, right? So my problem was, what's the follow-on act? But what was happening at the rest of USC was work that was a little more closely and increasingly closely tied to other aspects of society. So you saw the rise of the natural language work. You saw the rise of AI, which one of the things that AI has been very cyclical, right? So AI is one of those problems that everybody thought at the beginning was going to be much easier than it actually is, right? So, back in 1985, AI was going to be done in 5 years. No problem. And ISI had early strength in that space. But I think that one of the things that's happened since then is, there have been some, as everybody understands, some really significant breakthroughs in kind of the intellectual underpinnings of what I would now call machine learning, which is a small subset of the broader field of AI, but it's the one that is dominant right now. And that was a tremendously enabling technology for all sorts of uses, right? So, many of the strength of AI is taking that enabling technology and applying it across the board to, some of the work, the human trafficking work that you probably are going to pick up somewhere, some of the sort of the misinformation management works, that kind of thing, the natural language in general. Really what that's doing is it's bringing these kind of cutting edge machine learning ideas out of the pure laboratory environment and into a more practical place. I would say that the field of computer science as a field established itself in the early 1960s. And very, very, the dawn of what we now call computer science. I don't remember when the Stanford AI Lab was founded, but it was probably 65 or so. The MIT AI Lab was founded around the same time. And before that, computer science wasn't a thing, right? Physics is 300 years old. Chemistry, we didn't call it chemistry at the time, but it's 2,000 years old, right? Computer science wasn't really a field. The idea that computer science would be its own intellectual discipline was really established. I give a lot of credit to a guy named J.C.R. Licklider, who was, kind of a famous, he was the first technical director of DARPA. He saw the opportunity to create labs, things like that. ISI wasn't quite at that dawn of time, but it was darn close, right? So the thing that's really important to understand is when you're young, everything's really easy, right? Everything is low-hanging fruit. And everything you do is new. And everything you do is big. And some of it doesn't work. And it gets buried. You'd get the shovel out and bury it in the mists of time so that everybody forgets it didn't work, right? But ISI was in the fields that it was in at a time when you could have tremendous influence by doing, sort of basic early things. So now the field's growing up, right? And we can talk, it's interesting to talk about exactly, where it is in its life cycle or what that means. I sometimes call it a teenager, right? Sometimes people throw stuff at me when I say that, right? But, this whole field of information sciences, computer science, it's not a hardcore structured discipline like physics is, So if you're going to become a physicist, first of all, there's fascinating stuff to do, and obviously, we're learning about, sort of composition of matter and how the universe works and things like that we don't know yet. But the discipline is established. The processes are established. The procedures are established. A lot of the work is kind of taking an incremental step, systematizing our knowledge, things like that, right? So when computer science was young, that wasn't what it was about at all. It was about, what can we do that we've never done before? So now the Institute and the field in general are in a different place. And I think that ISI has as much to contribute in that place as it did in the early days, in the place that the field was in then. And I think a lot of that contribution comes from the fact that, as computing has become, kind of fundamental underpinning of society, you have to approach the problems differently, right? You have to come in and say, look, I love to sit in my basement and hack on this computer, but, did I accidentally break the stability of a society? And did I create a way to spread misinformation at the speed of light and thus destroy 1,000 years of what we know about how government works? Well, yeah, actually we did, right? So that's a problem. I think that the next wave of the Institute will be to look at these problems in a larger context. And I think that that's a transition that's happening now, right? So it's not done. It's a very difficult transition because not for ISI, but for the field, right? Because the expectations that are being put on the field are changing. The culture is changing. An interesting example from a few years ago, broad example, there was a moment in time up to, depending on where you were, maybe the mid-90s, where the only way you could become a tenured professor in computer science was to have some individual accomplishment that you could point to. And say, look, I did this, me and my students, right? But I invented this, or my students and I did that, right? And now it's much more about collaboration. It's much more about interdisciplinary research. It's much more about how your intellectual innovation ties into some larger problem that we have. Here's an interesting example. We're about to have a disastrous crisis because of the death of antibiotics. Antibiotics changed the world, right? Before we had antibiotics, your chance of surviving to adulthood was half of what it is today, whatever. I made the number up, but it's something like that. People died horrible deaths from infectious diseases. Pretty much everybody alive today takes advantage. They just assume that, I cut myself. I'm going to take some penicillin or whatever, right? Not I cut myself and I'm going to get gangrene and die. But there's a problem that antibiotics are becoming, the bacteria are becoming resistant to antibiotics, right? So antibiotics are less and less effective. This is a trend that's been going on for a while, but it's about to be a real crisis. And we've gone through all the ones that are sort of the cheap, easy ones. We're now, the antibiotics of last resort are terribly damaging to your liver and all these things, but they'll keep you alive, maybe, except that even that's challenging. So what do? Well, it turns out that machine learning and AI are pretty good at inventing antibiotics. So this is a new thing. Just in the last few years, the folks that have been trying very, very hard to find new antibiotics are now trying to apply machine learning to this problem. And it's early days, but it would appear that this is likely to create a revolution in our ability to stay ahead of the fact that bacteria are actually very smart, although somewhat small, and pretty good at evading antibiotics. And maybe with the application of machine learning to the drug discovery process, we'll be able to, there are two different ways, right? One is we'll be able to invent new drugs. And the second is we may be able to use machine learning to understand interactions, powerful positive interactions between different drugs that will allow us to treat diseases in novel ways using drugs we already have. The fundamental technical ideas that underpin the internet are actually very simple. And in fact, that's one of the reasons they succeeded, is because they're simple. But these ideas, a lot of people did the early work. The technical approach that the internet uses, it's called packet networking. It's different than what we used to do. But that's not why the internet worked, right? That's why it was a technical success. But the reason it worked is because of the style of development and the style of interaction that people came. So the idea then, there were many competing technologies, right? You know, everybody who was, you know, making computers or whatever figured, well, I want people to use my networking protocols, right? And I want to lock them into this proprietary protocol that we've got because, you know, if I can get everybody to sort of buy into my networking, then they'll buy my computers, right? And if they wake up tomorrow morning and want to buy somebody else's computers, they won't be able to because that computer doesn't do my networking and they've already got my computers, right? So the internet community, the people that were sort of pushing the internet, came along and said, no, let's not do that. Let's create an open process. Let's create a method of working together and a whole sort of social structure that allows us to develop this technology in a way, first of all, that everybody that is part of it will be able to contribute to, and secondly, we're going to make it open to the world. So I would argue that this is actually the first hint of this idea of this thing that's come to be called open source, right? And the notion that, you know, giving away your technology, your standards, is ultimately a more beneficial and influential approach than trying to commercialize it or monetize it. I think that the people who are sort of the early progenitors of the internet ideas understood that, maybe somewhat intuitively. But the person who I think really brought it to fruition, in a sense, is Jon Postel. His major contribution to this is that he's the person that really brought together the process that caused the internet standards to happen, right? So the internet, in a very weird and sort of you know, self-deprecating way, the internet standards documents are called requests for comment, right? This is confusing as hell to the world because they're the requests for comment series, the document series, right? It's a series of documents that are published by this thing called the Internet Engineering Task Force. And some of them are actually genuinely requests for comment, right? You know, you write a thing that says, we're thinking about this, what do you all think of it, right? But some of them are the actual standards, the technical standards documents of the internet. But if you call them standards, that's kind of harsh, right? So instead, they were called requests for comment. You know, the process of developing those and publishing them and how they came about became more and more formal over time. When this whole thing began, it was an informal group of people that, you know, that wrote these documents. But as the process formalized, and as it became a little more structured, Jon was the guy who was really in the middle of it, and he was the person. He was for some time the request for comment editor. It was Jon's job to make sure that people's ideas were represented and came together and presented coherently, and that everybody sort of got focused and working in the same direction. So, you know, if you're talking about creating the concept of open collaboration, Jon's the guy who kind of brought the whole process together. And it was a very, very astute combination of understanding process that worked for sort of socially, to bring some very, very, you know, strong-willed and strong-minded people together. And because he had the technical depth, he could command the respect of all the other people. So, you know, that's the role where I would say ISI is the unique contributor. You know, the technology of the internet over time, ISI certainly contributed. It contributed in very interesting ways. But so did BBN, so did MIT, so did University of Utah, Stanford. You know, you can rattle these people off at different times, right? But the sort of social role that caused this amazing development process that led to this industry came out of ISI. I was talking before about the idea of general purpose. The idea that we were building this network not because somebody knew exactly what they wanted to do with it, but because the whole idea was that it would let you do things that you didn't even know you wanted to do. So this is a really good example of that. Right? So the technology that turned into the internet, it was originally designed for this class of uses that I talked about that they would describe as reliable communication. Right? So if I send you an email, I want it to get there. If you get a file from some distant thing, you don't want it to, you know, you don't want the letters to change. You'd like it to actually say what it's supposed to say, right? And that's more important than having it happen right away or quickly or whatever. It's the reliability that's the first point. So early on, people recognized that there were other kinds of applications for where that wasn't the big deal, right? Where the big deal wasn't that it had to be perfect, it was that it had to happen right now. So me talking to you is an example of that. Right? If I stutter or, you know, spit my coffee through my nose or something like that, you'll still understand what's going on. The very earliest design of the net laid a little bit of groundwork for doing that. But it wasn't what people were pursuing. So then along came a set of folks, and notably at ISI and BBN, who were actually very interested in this other kind of application. And this, the starting point was sending voice, being able to talk over the network. And there were competing views about how to do that. So each of these competing views, these are sort of, deep technical questions, and it's not something you could really describe in a short time. But both of those views set out to build an example, and that was one of the sort of guiding philosophies of this internet work. All of this internet work was there's a very famous saying that Dave Clark. It's a quote from Dave originally. It's rough consensus and running code, and that's how progress was made in this community, right? You try to get as much agreement as you can, and if you can build it and show that it works, that's your high leverage, right? So a bunch of folks at ISI set out very, very early to try to build tools that let you use this kind of human-to-human communication over the network. And the version of that got an early start turned out not to be the one that succeeded in the end. So it's a very good example of this kind of competition among ideas playing out. But really, as early as the late 70s and early 80s, you saw people thinking about this. And at the time, there was really a lot of skepticism. It's one of these things that seem very easy to us today were very, very hard to do back then for any number of reasons. Computers weren't very fast, the network wasn't very reliable, all these things. But you saw this development. And, back in maybe as early as 83, 84, you started to see prototypes about this. But the next idea that came along, which is the one that I think actually changed the dynamics tremendously, if you think about something like email or remote login, it's from one place to another. It's point to point, right? Me to you, her to him, something like that. But when I'm talking about human communication, it's often one person to a whole group, or a whole group of people chatting with each other, or something like that. It's technically we use the term multipoint or multicast. And so that's a whole different kettle of fish, because now what I want to do is not just send something from me to you. I want to send something from me to everybody, and from you at the same time to everybody, including me, and so on. And so it's a whole new kind of fundamental technical idea. We had this idea at the time that we would be able to use the same network to do all of these different sorts of data transport. That we would be able to use it for voice, for video, for classical data transfer, like moving files around and stuff like that. And instead of needing a separate network for each of these uses, we'd have one network that could do them all. And so this was a pretty radical idea at the time, because the characteristics of these uses are so different that there was very widespread belief that you would have to build a separate network for each one. And the telephone companies had invested billions of dollars in building their networks, and they weren't too happy with this thought. So this was a line of work that was pursued very heavily at a number of places, including with ISI as one of the leaders. As I said, I'm from, I would say, probably the late 80s to the sort of mid-90s. We went to DARPA and said, look, we have this very interesting idea, but we need a platform on which we can do the research. And we need to be able to give the researchers that are going to be working in this space a network that they can break, right? The issue is that by this point in time, the internet had become very important to normal uses by the people who were using it. So you couldn't turn it off. You couldn't break it. You couldn't say, well, I want to change this little bit of it and see if it works better for this purpose. And this is the first evidence of success, right? Is that if something gets so important that they won't let you break it anymore, you've actually succeeded. So we went to DARPA and we said, we would like to build another little small network just for these researchers that we can break and work on this new set of ideas. And they said, this is a wonderful thing. We'd very much like to support this. Allison Menken, who was at ISI at the time, was really the leader in pulling this together as a testbed. And so we built this little network. It was called DARTnet, which stands for DARPA something network, and went down this path of what became the next, a next big generation of internet applications. So, here we are in it's 1990, and video is little postage stamp things. It's not like we have big high-res cameras or anything like that. But a set of video conferencing tools were designed and built. This idea of multicast communication became very fundamental, and that represented a whole new generation of the internet protocols. And that is really we don't use quite the same technology today that was developed then, but that's the logical, father of ideas like Zoom, of ideas like video streaming. And the thing that happened in the mid-90s, when this technology became solid enough that you could use it without having to fix it every 10 minutes, is that we started having, foreshadowing the future in a remarkable way, we started having some of the meetings of the research groups over these tools. So it became possible for the first time to sit, in an office in Boston and have a conference with people at ISI and people at UCLA and people up at Stanford or Xerox PARC, or the Lawrence Berkeley Lab was heavily involved in some of this. And and it was it worked. You could use it. But this is a very interesting thing, because it shows sort of the multiple generations of work that have gone into this internet, and it shows the power of the very early ideas and the focus that the early ideas had on making something general purpose, and the fact that we've been able to leverage that for sort of many generations. If you go back to what I've been saying about the process that led us to the internet, and the fact that it was, really a collaborative process, and what we were doing there was we were focus. It wasn't me. I don't want to take credit for this, but people like John Postel, it absolutely was. We were really inventing a kind of a new way for people to work together on technical stuff. But an interesting artifact of that is it was assumed that it was going to be used by a community of people who were kind of all on the same side. And the flip side of this collaborative working model is you don't really assume that there are going to be a lot of hostile people in the room, right? And it's not the case that nobody thought about cybersecurity on day one. But it is the case that some decisions were made, either formally or implicitly, to not put a lot of weight on it in day one, on the thought that maybe it would be better to get something working and demonstrate the possibility, but also honestly on the thought that the network would never get big enough for it to be an issue. So this is a case that I would say was a little bit of a failure of imagination. And the result of that is that there are a lot of places in the early design of the internet where we did not really assume that there were going to be malicious actors in the game. So that the history of the network and its evolution goes through sort of three parts. There was the earliest days when it was, the ARPANET, and you had to be government sponsored to connect to it, and there were 50 people and whatever. And then there was a period of time when it was still a government project, but it was much bigger. So there was a period of time we had something called the NSFNet that was sponsored by the National Science Foundation, and their idea was they were going to connect all of the research communities together and so on and so forth. But it still was not really focused on commercial use. And then there was a transition when it was opened to commercial use. It became very obvious that that was the right thing to do from a number of reasons, ranging from the fact that it was tremendously powerful and would advance the country, to the fact that if you let commercial people use it, they would pay for resources, which was really cool. And so, that's the beginning of the shift to a point where understanding security and understanding, I like to think of security, the true cybersecurity people hate this, but I like to think of it as a sort of subset of robustness, right? The network, any technical structure like this, it's not just the internet, but any technical structure needs to be really fit for purpose. And that means needing to take societal issues into consideration. So a good example of that is the assumption that not all the people connected to an internet are on your side and trying to be your friend, right? Another example of that is that machine learning algorithms can be unintentionally very biased if they're not trained right. So we see all sorts of cases where fitness for purpose includes taking into account larger societal forces. And the evolution of cybersecurity is one of those cases. So now, suddenly, where now is, I don't know, maybe the early 2000s, we're playing catch up, and we're noticing that the internet protocols maybe weren't designed with security in mind, particularly commercial needs. And we're noticing that, if you're going to have an open network and pretty much allow anybody to hook up to it by, buying service from Comcast or whatever, that your resilience to people who are malicious or just accidentally have configured their computer wrong and don't know any better needs to be high, right? So this is a place where I would say this is a place where current research is trying to turn a corner. So, we have been approaching this problem for a number of reasons, kind of from a narrow perspective and kind of from a reactive catch-up perspective. Can we add security in places that it wasn't? We don't want to throw the whole thing out and start again for two reasons. One is that would be very painful, and the second is I'm not sure we'd know quite where to start. But the sort of tone of cybersecurity research is in the process of changing, in my view, from this kind of reactive and narrowly focused thing to a more holistic and more proactive approach, where we're really trying to understand how to build systems that are robust and secure by nature, as opposed to having it patched in. And that's oversimplified, of course. But this is a research of the moment, and it's a fundamentally very, very hard problem, right? Because understanding what makes a system like this secure. I've suggested in what I've been saying all along that, when you get into something like the internet where it's embedded everywhere, it's really a mirror of society at large. And so I need to understand what it means for the society at large to be secure, and then reflect that into this network. And there have been a number of approaches, some of which are very naive, and some of which are things we don't really want. So, there are people that think that if only I could put your name in every packet that was sent over the network, then I could know exactly who to blame if something, went wrong. But on the other hand, we value anonymity at times, and we value the ability of people to speak freely in cases where it might put them at some risk. So we don't, there's a tremendously balancing problem here. And we really are, this is kind of a big question of the day. This observation that once you get out into the real world, cybersecurity becomes a much more challenging problem. And what we're really trying to study is not just a technical problem. I think one of the big issues that a lot of technical cybersecurity researchers have is that they think that purely technical answers to much more complicated problems are achievable, right? And really that's not what you're looking for. What you're looking for is kind of technology integrated into a larger picture. So I want to tie this all the way back to the darknet that I talked about a minute ago. So we're trying to invent this interesting new world where human communication can be part of the network. We don't have that world at the time, and so what we wanted to build was a little small second world, right? We're trying to do something that we hope will be true in the future, and we need to sort of enable the future today by building a little playground. So now if I fast forward, you'll notice that I've actually got the same problem again. I want to study cybersecurity in a world where I can't change the whole thing. I need to build myself a little playground. And that's what, building, that's a thing that is a real historical strength of ISI. So I spoke about probably the earliest example of that. But in, I guess, probably 2003, 2004, we set out to do the same thing in the cybersecurity domain. I had not quite joined at the time. I walked into this project. But this is this thing called the DETER testbed. So it's a catchy name because you need a catchy name to raise money. But the idea of this was to build a playground for cybersecurity researchers that could model important parts of the real world and let them fiddle with it, right? So there are two separate uses for ideas of this sort, and they're both very important, but it's really important to understand that they're different. One of them is, I want to test ideas and see if they work in today's world, right? So if I have some kind of interesting, theory about cybersecurity and I want to try to launch a massive attack on the Bank of America to see if my theory is any good, well, the Bank of America doesn't really like that very much. And so what I need is a little playground that models today's world accurately so I can try out ideas. But from my point of view, that's actually much less interesting than the other use, which is to create futures that don't exist yet. So if I want to build little models of a possible future, so I can try them out before we get to them for real, that's a very important part of research. And it's a place that ISI has developed significant strength. So this thing called the DETER was set up. It's been a project that was funded for almost 15 years by the Department of Homeland Security. And it started in a very sort of naive way. It started, we borrowed a bunch of technology from a thing that the University of Utah did called Emulab. But very quickly, we started expanding it. And Tyree Benzel was the principal investigator for this. I was, for some time, probably the chief scientist or something like that. And what we were setting out to do was build a model of the world in a way that was accurate enough for people who were trying to do cybersecurity research to try out new ideas, and particularly to try out these more holistic ideas that I spoke of, before actually trying to spring them on the public at large. And that project became increasingly sophisticated over time, and then it's kind of forked. And now we have at ISI a number of test beds that have been built for different research purposes and different projects. And each one is focused on creating a little model of the world, either of the present or the future, that's what's needed for that project. So one of the neat things about DETER that made it very special at the time we did this was that you could model some things very, very accurately and some things less so. Right? So you don't have enough computer power to model the whole world, because you just don't, right? That's not how things work. But if I can take my computer power and sort of move it around to make my model, highly accurate in places that it matters and less so not, then I can do really interesting science that we don't otherwise have the ability to do. And so that's work, that is continuing at ISI today. It's continuing to be developed. And I think it's going to, over time, directly tie to this thing I talked about before, about the transition of cybersecurity from kind of a purely technical, somewhat narrowly focused effort that in some cases is very reactive, to a much more proactive effort where we're really starting to understand in a fundamental intellectual way how to build systems that we can trust. So as the field grows up, as computer science matures, and it's on some life cycle path, it's on some path to the future that we don't know where it's going to go, but we do know it's sort of halfway there. ISI is almost unique in the computer science firmament because it is it's a very capable research lab. It has the ability to bring significant resources to bear on projects, on research efforts, and it's tied to a leading academic institution in the information sciences area. So we have PhD students, we have faculty advisors who are, charged not only with doing their research, but with mentoring and creating the researchers of the future. And it's tied into the rest of a university that has all of these other areas, right? So we have faculty members whose home base is in the School of Journalism and are studying misinformation and disinformation, things like that. You'd never do that in a classic computer science department. You wouldn't have the right balance of skills. We have people who are tied into the medical school and are positioned to work on, the things that I spoke before about, for example, using machine learning to invent new medical procedures and treatments. So it's really this very unique combination of a dedicated lab with the ability to do large, sweeping things, if that's what's needed, the tie into academic computer science, so we have the ability to intellectually advance information science and computer science, data science as a field, and the tie-in to all of the larger forces that are trying to shape the field, or that are needing to shape the field, as information science matures into a sort of underpinning of society, as opposed to just a really cool thing to do.